exam. I'm super excited to go through the electric circuits part, but let's start slowly with thermodynamics. So when it comes to thermodynamics, we need to talk about the difference between Celsius and Kelvin, right? The scales. Now, Celsius is essentially used in Europe, Australia, and actually most of the countries around the world. However, the United States of America use a different measurement, system, which is called Fahrenheit. Now, Fahrenheit obviously measures things between 0 to 100 degrees, or even negative, but the thing with Fahrenheit is that 0 means things are really cold and 100 means they are really hot, which kind of makes sense intuitively at first, but not always. There is also Celsius, where 0 degrees is fairly cold outside and 100 degrees is essentially you're gonna be dead. Kelvin, whether it is 0 degrees in the Kelvin metric system, whether it is 0 degrees or 100 degrees, those are unlivable conditions. Neither of them, right? Why? Because it's super cold at 0 degrees Kelvin and really, really hot at 100 degrees Kelvin. But how do we convert between Celsius and Kelvin? Because scientists use Kelvin and not Celsius. Well, first of all, no one uses Fahrenheit. It's not necessarily the best. Obviously, I am not American, so I can't give a lot of insight when it comes to Fahrenheit. But for VCE in Australia, you don't really need to know, at least to my knowledge, how to convert between Fahrenheit and Celsius. But you do need to know how to convert between Celsius and Kelvin. Now, to convert between Celsius and Kelvin, the only thing you have to do is to whatever degree you have in Celsius, you add 273. Let me give you an example. So, let me access my pen. Now, if it is 5 degrees outside, 5 degrees Celsius outside, what is the equivalent temperature in Kelvin? In order to find the equivalent temperature in Kelvin, all we need to do is add, say, 5 degrees Celsius plus 273. That would be 278 Kelvin. So the general formula in order to convert from degrees Celsius to Kelvin is temperature. The temperature in Kelvin is equal to the temperature in degrees Celsius plus 273. That's all. Let's look at another example. At 100 degrees, let's say a question states, what is the boiling point of water in Kelvin? Well, the boiling point of water in degrees Celsius is 100 degrees Celsius. You add 273 and the resultant would be 373 Kelvin. that also means that the freezing point of water would be, in Kelvin, it would be 0 plus 273, which would equal 273. So the freezing point of water in Kelvin is 273 Kelvin, and the boiling point of water in Kelvin is 373. Which is awesome, right? Wait a second. But what would be the lowest possible temperature in degrees Celsius? Because we know that 0 degrees Kelvin is the lowest possible temperature that scientists at least have achieved so far. They haven't really achieved it, but they've come close to. Well, we can use this formula here. We can rearrange to find the temperature in degrees Celsius by subtracting 273 from the temperature in Kelvin. So if 0 degrees Kelvin is the lowest temperature that we can achieve, or at least the lowest temperature that exists, subtracting 273 from it would leave us with negative 273 degrees Celsius. So in degrees Celsius, so just to put everything into perspective, negative 273 degrees Celsius is the lowest temperature possible. 0 degrees Celsius is the freezing point of water. 100 degrees Celsius, 100 degrees Celsius is the boiling point of water. In Kelvin, 0 Kelvin is the lowest possible temperature. 273 Kelvin is the freezing point of water, and 373 Kelvin is the boiling point of water. I hope this kind of puts everything into perspective. Now, let's look at some of the laws of thermodynamics. First of all, we have the zeroth law. The zeroth law states that two bodies in contact with each other will come to a thermal equilibrium. That is, if object A and object B are in contact with one another, and B is in contact with object C, then the temperature of object C when everything comes into equilibrium will equal the temperature of object A, right? In fact, A, B, C, and A will all have the same temperature when equilibrium is achieved. So let's look at the first law and then the other laws. The first law basically is referring to the conservation of energy. So the zeroth law is referring to every body that is in a particular system in contact with one another. When everything comes into equilibrium, every single body that is involved in this equilibrium will have the same temperature. And in fact, that is the definition of what equilibrium is. The first law is stating that energy is conserved. In an isolated system, heat energy is the internal energy of an object plus the work which is done by the system. Internal energy is the energy associated with the random motion of molecules. For example, let's think of this part as, let me explain it in this way. Think of water in a container, in a pot. Water in a pot, essentially, the heat energy, it would be the internal energy, right, of the water molecules, because we know water is a fluid, therefore the water molecules are free to move around. That means that the water molecules themselves have internal energy, and this is the energy of vibration. So essentially, that's the internal energy of a system in that regard. Now think about another example. So that's the first law, stating that the total energy of the system is whatever the internal energy of the water is, plus work which is done by the system, right? So whatever additional energy that we input into the pot of water, for example, heating it up or whatever. It doesn't matter, the rest, right? So that's the first law, law of conservation of energy. Also, the second and the third law are discuss entropy a bit more, and we're not gonna cover that now, if that makes any sense. Now let's talk about the zeroth law again. When we are talking about the zeroth law has to do with, let's say we have a mug, right? It's a cup of tea. Let's assume it is a cup of tea. And you use a spoon to swirl the tea around. There are three objects which are in contact with each other. There is the teacup, there is the spoon, and there is the tea itself, the water. Now, initially the tea will be very hot. The cup will be at room temperature and the spoon will be at room temperature. After, let's say, 15 minutes, the thermal energy of the tea will be transferred to the cup and to the spoon. Therefore, after 15 minutes, the temperature of the spoon and the temperature of the cup will increase, whereas the temperature of the tea will start to decrease. And therefore, everything will come into equilibrium. But how is energy transferred? Alright, so we learned about the units of measurement of temperature, which is the units of measurement of temperature, which we said, we're going to use Kelvin and we're going to use degrees Celsius, but we are not going to use Fahrenheit. Cool. We learned about the zeroth law and the first law, which essentially both of them are kind of emphasizing the law of conservation of energy, right? Energy cannot be created nor destroyed, it can only be transformed from one form into another. That is, if you put hot water into a cup, essentially the cup will eventually become hotter because you've poured hot liquid into it, and the liquid will essentially cool down because you poured it into a cold cup, right? So everything will come into equilibrium eventually. Now, there are different ways through which heat energy can be transferred. These are convection, conduction, and radiation. Convection is essentially the process by which hot water particles will flow to the top, while colder water particles will flow to the bottom. And it doesn't really have to only be with water. Obviously, it can be with currents. For example, a hot current can flow to the top, while a cold current can flow to the bottom. Conduction, on the other hand, has to do with the fact that particles in the medium will pass along the heat to the particle that is adjacent to it. So I think, first of all, let's emphasize again convection. Convection is hot current moves to the top, cold current moves to the bottom. Conduction, however, has to do with the fact that particles, for example, in metal, right, are adjacent to one another and they vibrate while maintaining the same relative position. While they vibrate, they will pass on energy to the adjacent atom, and then that atom to the adjacent atom, and then the other one to its neighboring atom, and then that atom to another atom, and that atom to another atom. And it is in this way that heat energy is transferred along atoms and along from one object into another. There is also another form through which heat energy can be transferred, and that is radiation. Heat is passed along without requiring a medium. In this case, objects which have a relatively high temperature or any form of temperature will emit something that we refer to as thermal radiation. Now, thermal radiation is a form of transferring energy from one object to another without a medium. What does that mean? That means that there is no need for a medium to be there, or in other words, you can transfer heat energy via thermal radiation even in a vacuum. And that is really important because that is essentially how Earth heats up with energy from the sun. Now let's talk a bit more about thermodynamics and energy inputs and temperature. There is something that we refer to as the specific heat capacity. The specific heat capacity is the amount of energy required to increase the temperature of an object by 1 degree Celsius. Did I say? Let me say that again. The specific heat capacity is the amount of energy required to increase the temperature of an object by 1 degree Celsius. The latent heat capacity is the amount of energy required to increase the energy of a gram of mass by 1 joule of energy. Now, that statement is not fully correct, I have to be honest. It is a bit more complicated, the way that the latent heat capacity works. Because it involves bonds breaking and change of phases for a material. The two equations that you see here, both of them have to do with the fact that, well, when we're boiling water, let's say we have a solid cube of ice, we melt it into liquid water and then we boil it into gas. Well, obviously we are inputting energy at each stage. These equations are designed to help us understand how much energy are we putting into water, or how much energy is water absorbing to move through each stage, or how much energy is the water absorbing at each stage, even if it isn't moving between the stages, right? Well, let's start with the first equation. Let's see and let's learn how to calculate the amount of energy that water is absorbing at each stage. First of all, this equation, Q equal to mc delta T. Q is the energy which is measured in joules or kilojoules. M is the mass, which is measured in kilograms or grams. C is the specific heat capacity. For example, 4.18 per joules degrees Celsius kilogram degrees Celsius. Delta T is the change in temperature. M is the mass, L is the latent heat of fusion. Now, let me double check the specific heat capacity of water. The reason I have put the kilograms or grams, joules or kilojoules, it's because you can actually convert between them, that's why. So yes, yeah, you can use kilograms. It's 4.18 times 10 to the power of 3 actually. Joules per kilogram degrees Celsius. The latent heat of fusion. The latent heat of fusion is the amount of energy required to melt an ice cube into liquid water, and I think it's around 3.3 times 10 to the power of 5 joules per kilogram. Don't quote me on it. And the latent heat of vaporization, I think it's like 5 times that, around 22 point something joules per kilogram. And then gas obviously has a different specific heat capacity. In fact, if I were to, so now that you guys, I think, understand what each of these is, right? So Q equals to MCAT, it's referring to the amount of energy required to heat up ice, or to heat up water, or to heat up gas. So this equation, it's used when we're trying to identify how much energy is an object absorbing while it is maintaining the same state, the same physical form, right? Whereas the second equation here, with the latent heat of fusion or vaporization, that is the amount of energy that an object is absorbing while changing states, but the temperature isn't changing. Let me explain. So when let's say we have a ice cube, right? We have a cube of ice, and we want to melt this cube of ice. What do we need to do? Well, obviously we need to warm it up, but up to what temperature, right? Well, the freezing point of water, it's actually 0 degrees Celsius. So as long as the temperature is above 0 degrees Celsius, the ice cube will start to melt. Cool. So let's try and melt the ice cube, right? Now, while we melt the ice cube, obviously, let's say we have it in a room at 5 degrees Celsius, right? Given a certain mass of the ice cube, let's say 1 kilogram, and given the specific heat capacity of the ice cube, for each unit there is a change in the temperature of the ice cube, not the room temperature, but the temperature of the ice cube. This is what this change in temperature is about. For each change in unit, for each change in degrees Celsius, for every 1 degree Celsius that the ice cube is gaining, the more energy it is absorbing. And that makes sense, right? The more heat energy the ice cube is absorbing for an increase in temperature. So as the temperature increases of the ice cube, right? As the temperature of the ice cube increases, obviously the more energy it is absorbing, and it makes a lot of sense, right? Because that's what thermal energy is. I mean, we use temperature as a unit of measurement for thermal energy, as an indicator of how much thermal energy something has, even though energy itself is measured in joules. Temperature can actually reflect whether an object has a lot of thermal energy or not, right? So if an object is really, really hot, obviously it has a lot of thermal energy, and if it's really cold, it doesn't have that much. So temperature, it's really good in that regard. So if our ice cube is initially at a temperature of negative 10 degrees Celsius, and it's gaining 1 degree Celsius and 1 degree Celsius and 1 degree Celsius up until it's negative 7 degrees Celsius, and then negative 5 degrees Celsius and negative 3 degrees Celsius, and then eventually 0 degrees Celsius, as the temperature of the ice cube is increasing, it's gaining more thermal energy, and we can measure this amount of thermal energy that the ice cube is gaining by using this equation here. We have to input the value again of the mass of the ice cube, the specific heat capacity of the ice cube, and we have to put in the delta T, which is how much is the temperature, or how much has the temperature of the ice cube changed from negative 10 degrees to 0 degrees. So the temperature has changed by 10 degrees, right? So if we have 1 kilogram by the specific heat capacity of ice multiplied by 10. That's how you find the total amount of energy, that the ice cube has absorbed up until this point. How about this part here? Well, during the melting stage, the temperature of the ice cube, the temperature of the ice cube will not change, even though it's gaining more heat energy, right? The temperature of the ice cube will not change, even though it's gaining more heat energy. Why is that? Well, the ice cube, obviously, it's a crystal lattice, where bonds are formed in an hexagonal shape between water molecules because of strong hydrogen bonding, right? So these bonds need to be broken. In order for the bonds to be broken, the intermolecular forces of attraction between water molecules need to be broken. You need energy to break these bonds, right? But now let's first of all understand how the crystal lattice is formed. Now, if you think about water, water has the formula H2O. Now, water is made up of an oxygen atom and 2 hydrogen atoms. The oxygen atom has a very strong affinity for electrons, and it will absorb these it will attract these electrons towards itself. Therefore, it will form a relative negative polarity towards its end. Then, towards the end of the hydrogen, that would be a relative positive polarity. That is, the water molecule itself will be a dipolar molecule with one negative pole and one positive pole. However, if there are a bunch of water molecules close to each other when the temperatures are really low, what will happen is that the hydrogen of one molecule will start to form very strong electromagnetic forces of attraction with the oxygen of another water molecule. And how does that happen? Well, that happens because, remember, this end of the oxygen, right, this end of the molecule towards the oxygen end is negatively charged. It has a negative polarity. So you have a positive polarity and a negative polarity. These opposite poles will start to attract each other, just like the North Pole is attracted towards the South Pole, right? The North Pole of one magnet is attracted towards the South Pole of another magnet. It's the same thing with electrostatic forces of attraction. It works in the exact same way. However, this happens with all water molecules, right? With all neighboring water molecules, they will start to form bonds with one another, right? They will start to form all these bonds with one another until they form this hexagonal crystal lattice. And this is what an ice cube is, essentially. And that's why snowflakes have those very beautiful shapes, right? Sometimes they have those really, really beautiful specific patterns. That's why, because water, once it freezes, the water molecules will arrange themselves in a hexagonal form. When you increase the temperature, right, all that you're doing, right, so let's say the temperature is negative 10 degrees here, and the only reason I'm spending so much time with this because I'm pretty sure you guys understood the gist of these two equations. One measures the amount of energy that something absorbs while it is in the same state. The second equation measures the amount of energy something absorbs while it is transitioning between states. But I really want to make sure you guys understand the graph because it is really, really, really important for your future studies, whether it is year 12 or whether it is at uni. And obviously, I'm having issues. So, if the temperature is negative 10 degrees Celsius, here at the bottom, and we increase it to 0 degrees Celsius, it's still, again, water will still be in the form of an ice cube, right? It will still be in the form of an ice cube. But all that's happening is that the water molecules are starting to vibrate more and more and more and more. It's still an ice cube because, again, ice doesn't melt until it reaches 0 degrees and above, right? So at any point below 0 degrees Celsius, the ice cube will maintain its shape. As we increase the temperature and the water molecules start to vibrate more and more in this lattice, again, the heat energy of the ice cube will increase. So the heat energy, as you can see, it's almost a linear graph if you ignore, again, those two stages. right? So the heat energy that an object has is actually proportional to a certain degree with the increase in temperature. And that makes a lot of sense, because as we increase the temperature, obviously we are increasing the heat energy that is stored in an object. But the difference now comes here, during the melting stage, because during the melting stage, the vibration between the water molecules has increased so much that the bonds will start to break, the intermolecular bonds. Intermolecular bonds are the bonds that I mentioned before. They are the electrostatic forces of attraction between molecules, right? The electrostatic forces of attraction between molecules. I think I am starting to talk too fast now, but I'm getting excited about this topic. So these bonds are starting to break during the melting stage, and obviously, even though you are adding more heat energy, let's say by using a flame, you are adding, or by increasing the room temperature, even though you are adding more heat energy by increasing the by increasing the amount of heat energy, right? Even though you're adding more heat energy, the temperature of the ice cube, right? The temperature of the ice, or of the object, because that's what is on the y-axis, right? The x-axis is the heat energy that we are supplying to the object, or the heat energy that the object is absorbing, and the temperature is the temperature of the object, right? So even though the amount of heat energy that the ice cube is increasing, the temperature of the ice cube will not increase for a while. Why? Because all of this energy needs to be absorbed to break the intermolecular forces of attraction. And only after all bonds have been broken and all of this ice cube has been converted into liquid, only then and only then will the temperature of the ice cube keep increasing as we supply more heat to the water, right? And in fact, at this stage, it's not an ice cube anymore, it's liquid water, right? So halfway through, let's say we have supplied 10 kilojoules of energy. Again, this is just, don't take it seriously, but 10 kilojoules of energy here, 20 kilojoules of energy, and the temperature is increasing by 1 degree for every kilojoule of energy, hypothetically speaking. Between 10 and 20 degrees, the temperature will not increase at all. The temperature will not increase at all. Halfway through, it means halfway through in this graph, at 15 kilojoules of energy, half of the ice has been converted into liquid water. But still the temperature is not changing, right? After all the ice has been transformed into water, then will the water start to only then the temperature of the water will start to increase as we are adding more and more heat energy. And then the temperature of the water will increase up to 100 degrees Celsius with more heat energy. After that, the temperature of the water will stop increasing. The water will still keep gaining energy to break the bonds between each water molecule, make those intermolecular forces of attraction even weaker, until all the water has evaporated into gas. And only then will the temperature of the gas start to increase as the heat energy supplied increases. Does that make any sense? Or as the amount of heat energy absorbed increases, only after everything has been converted into the same state will the gas change temperature. So what does that mean? How do I simplify this again? Because I think it might sound a bit complicated. It's not a bit, but when an ice cube absorbs heat energy, let's say you're putting an ice cube on a frying pan and you have like a gas stove and you have like flames at the bottom. As the ice cube is absorbing energy, its temperature will increase. Then the ice cube will start to melt. During its melting stage, it will still absorb the heat energy because it's on a frying pan with fire underneath it, but its temperature will not change. Then once all the ice cube has melted into liquid water, its temperature will again keep increasing because again there's a fire underneath the frying pan supplying heat energy, and the liquid water is absorbing this heat energy. And then during the vaporization stage, the water will still absorb heat energy because again there is a flame underneath it. The temperature of the water will not change. Once everything has changed into gas, then the temperature of the gas will keep increasing, right? But maybe the frying pan example was not the best. The best example would be a pot with a lid on top. Because obviously if it's a frying pan, then things will escape. So imagine this stuff, but with a lid on top of it. The specific heat capacity is different at each stage, and the gradient here actually is indicating the specific heat capacity, or a property of the specific heat capacity. The steeper the gradient, the lower the specific heat capacity, because the easier it is to increase the temperature of the object by 1 degree Celsius, right? You require less heat energy to increase the temperature by 1 degree Celsius with a lower specific heat capacity, right? You need less energy. Therefore, a steeper graph. It's easier to melt ice than it is to convert the same amount of water from liquid to gas, right? And the same thing goes here. The specific heat capacity at each point will be different, but the specific latent heat of fusion, or condensation will also be different. In fact, this graph should be longer here because the latent heat of fusion, the water or the liquid water needs to absorb a lot more energy in order for all the bonds to be broken for it to convert into a gaseous state, in comparison to the bonds in the ice cube to be broken for it to convert into a liquid state. Keep in mind that this example makes a lot of sense if you think about the instance of having water in a pot and then you have fire underneath it. The thing is, things can go backwards as well, right? You can convert gas into liquid, and we call that process condensation. You can convert liquid into a solid, and we call that process freezing, right? So solid into liquid melting, liquid into gas vaporization, and then condensation is gas to liquid and freezing is liquid to solid. Now, this is a Maxwell-Boltzmann distribution curve. You don't need to know a lot about this, but this is trying to indicate how in a bunch of liquid or in a bunch of gas, there will be particles that have a lot of energy, and there will be some particles that don't have that much energy. The particles that have a lot of energy have a higher probability of escaping than the ones that don't. And that is the whole point with evaporative cooling. When something evaporates, it leaves the liquid. Particles with higher energy are more likely to leave. Evaporation decreases the amount of high energy particles, and evaporation therefore decreases the overall temperature of the system. And that is why humans sweat, or some animals sweat. The whole reason for us to sweat is because that's how we cool our body temperature down. That is what we call evaporative cooling. On the y-axis, we have the number of particles with kinetic energy E. On the x-axis, we have the kinetic energy. The white area shows the proportion of particles in the sample that do not have enough kinetic energy to react. Then we have the activation energy here. And then the blue area shows the proportion of particles in the sample that have enough energy to react. We can talk about the electromagnetic spectrum a little bit as well, because it does relate to thermodynamics, given the fact that we talked about one method of transferring heat being radiation. It means that scientists can use radiation to control how much heat energy they are releasing, if that makes any sense, or how much heat energy they can transfer from one object to another. And there are different magnitudes to the electromagnetic spectrum. There are radio waves, microwaves, infrared, visible, ultraviolet, X-rays, and gamma rays. Now, radio waves don't have that much thermal energy because their frequency is super low, but you can use them. We can use them for telecommunication. Microwaves, on the other hand, they are used to heat up particles. For example, they do have a little bit of heat energy. That's how we increase the temperature of food. That's why we reheat food. Basically, that's the whole point of a microwave. We microwave food, we increase the vibration of the particles. And in fact, fun fact, when you are putting food in a microwave, and you're gonna learn more about this later, but the waves that are being emitted, the frequency of waves is actually it matches the frequency of vibration of water particles, because a lot of food most of the time has water into it or a bit of moisture. Otherwise, right, like you're not going to be eating cardboard, right? So when the food has moisture in it and it's a good microwave, then the waves that the microwave is emitting are of a specific frequency that matches the frequency of vibration of water particles. And therefore, it will form a resonance. Once resonance occurs with the water particles, because that's what moisture is most of the time, it contains water particles. The temperature of the food will increase because the water particles are gaining more kinetic energy, and we know that kinetic energy increases with thermal energy. Then we can talk about the infrared radiation. Infrared radiation also, it can transfer thermal energy. So in year 12 physics, you will be required to know one use of infrared radiation, and the use of infrared radiation is that you can use thermal goggles to detect body heat from different animals or people, for that fact. The visible spectrum, it's visible light, ultraviolet light, I'm pretty sure most of us are familiar with. Obviously, ultraviolet UV rays can cause a lot of damage because they can increase the temperature of obviously they can increase the temperature of our bodies, but the problem with them, what I'm trying to get at, is that they can also energize nitrogenous bases in our DNA, and therefore they can cause free radicals to form. And when that happens, it increases the probability of cancer forming. X-rays and gamma rays do the same thing. In fact, they are very dangerous. You might need to know this equation. It's the Wayne and Stefan Boltzmann equation, where the lambda max is the peak wavelength in meters, B is Wayne's displacement constant, T describes the temperature in Kelvin, and it just shows that the power per unit of time, or force per unit of time, energy per unit of time, is directly proportional to temperature, and it makes sense. Now let's talk about the greenhouse gas effect for a bit, because then we have to talk about electricity, and I have a lot of questions to show you. The greenhouse gas effect, before we continue, I need to triple check if we're doing well with time, and we're doing beautiful with time. We're doing very well with time. The greenhouse gas effect is a very interesting one because it kind of encapsulates everything that we have learned about thermodynamics, where essentially rays from the sun are hitting the earth and they are reflecting back. But what happens is that this thermal radiation from the sun comes through the atmosphere, and then some of it will be reflected, but some of it will be absorbed again in the Earth's surface. When it is absorbed, it will heat up the surface of the Earth, of course. So the Earth itself will start to emit radiation. So Radiation comes from the sun, some of it is reflected from the ozone layer, some of it goes through, some of it is absorbed by the earth, and some of it is reflected back again. The problem is when there are a lot of greenhouse gases, instead of this radiation escaping back into the atmosphere, it will get trapped inside the earth, right? So radiation comes from the sun, it is absorbed by the earth, of course, and that is important. Otherwise, again, we don't want to go through another ice age, right? So that is important, that the earth absorbs sufficient amount of thermal energy. The problem comes when this energy, this thermal energy gets stuck between the atmosphere and the earth. And when it gets stuck in between those two layers, what will happen is that overheating might occur. And when overheating occurs, we don't have an ice age, obviously, but we have the opposite problem. And the opposite problem is actually a massive problem because a lot of life dies, and as the ecosystem gets ruined bit by bit, obviously it impacts our life as well. Now, what are some examples of greenhouse gases? Methane and carbon dioxide are massive ones. The problem with greenhouse gases such as carbon dioxide and methane, especially carbon dioxide, is that it increases the acidity of the water and the oceans, and that increase in acidity can be very harmful to life, let alone the heat, right? So think about the heat for a second. If the earth is overheating, the polar ice caps will start to melt, right? Once they start to melt, obviously the life on the poles will essentially die out eventually, right? Or it will have to evolve into something different. But when it comes to an increasing concentration of carbon dioxide in the atmosphere, that will cause carbon dioxide to essentially go into water as well, which it will increase the acidity of the water, and it will cause a lot of life to die as well, because obviously fish can't live in extremely acid environments, right? Like fish and other organisms, unlike bacteria, can't live in extremely acid environments. In fact, the pH has to be perfect, almost alkaline to a certain point. It depends on the region. But anyways, that's the problem with the greenhouse gas effect. And why do we call it the greenhouse effect? It's because just like a greenhouse that traps thermal energy, our atmosphere these gases that are released in the atmosphere are actually turning the atmosphere into that greenhouse, right? They're turning it into that impermeable layer, and the gases are essentially trapped.